Hello and welcome. Today we'll be looking at the measurement of voltages, amplitude, frequency, period of an AC waveform using the C.R.O, right? So this is our oscilloscope. Normally, when you on the oscilloscope, it should give you a straight line like this. If you don't get a straight line, you can check your settings. Maybe your position has been shifted, right? So you can't see it. You can also check the position for that particular channel you are using. We have channel 1 for the C.R.O. If you are connected your frequency generator to this, then you are using this channel. If you connect it to this, then you are using this channel. And then this is for extension. Okay, this is the extension. Okay, so that's a little on the C.R.O. Now let's look at the function generator. Now this only serves as a monitor. Okay, so whether you are checking the circuit as to whether your circuit is accurate or not, this can be used to do that. So it has a lot of functions. So as I said, this oscilloscope serves as a monitor, okay, to display whatever frequency or function you are generating. Okay, now we call this the function generator. This is the function generator. So this is what generates the frequency. This is what generates the frequency. And then this is the modern version of the function generator. This is the modern version. So back to the function generator. Let's say we want to generate a frequency of 98 Hertz, right? What we do is we have to check the range. We check the range first. Now this range, this particular range, this knob or button starts from 0.001 to 0.01. This one starts from 0.01 to 0.1. This one starts from 0.1 to 1. This one starts from 1 to 10 in that order till we get to 1 megahertz, right? So this is just the range. This is just the range. This is not the frequency. So if we are generating the frequency of 98 Hertz, the first thing we do is to check the range that 98 falls in. When we check, we can see that this knob starts from 10 to 100. This knob starts from 10 to 100. So we'll press this knob. So that's the range where we can find 98. Now, that's just the range. That's not the frequency. Now, to generate the 98, we tune this. So if you see, this is Hertz. This is the frequency. We tune this to 9.8. So this is 9.8, right? So 98 and then this range, this gives us 98 Hertz. Okay, let's try another one. Let's say we want to generate 1000 Hertz. We come back here. If we want to generate 1000 Hertz, we check the frequency, right? This particular knob has this one, it starts from 10, 100 to 1K. And then this one starts from 1K to 10K. So we press this. We press this knob because it starts from 1K to 10K. When we press this, the next thing we do is we put this on 1. We put this on 1. So this is our 1K Hertz. This is 1000 Hertz. This is 1000 Hertz frequency. This is 1000 Hertz. This is 1000 Hertz. So the next thing we do is to, let's say we want to generate, let me do the last one, we want to generate 250 Hertz. We come back here, we check this knob. Where can 250 fit? So we press this, because this range starts from 100 to 1K, so it means there's 250 in. Then we put this on 2.5. We put this on 2.5. So that's 250 Hertz. Okay, this function or this button is for the type of wave that you want, as to whether it's a sine wave, square wave, or a triangular wave. So if you want sine wave, you press this. If you want sine wave, you press this. If you want square wave, you press this. If you want triangular waves, you press this. And then this, we put it on 0. This is the attenuator, you put it on 1. This is the output voltage. The output voltage is the same as or is equal to the amplitude. Also, we can say that this particular function, the output voltage, is likened to the volt per dive here, right? So the particular channel you are using, if you are using channel 1, the volt per dive at the channel 1, the value there will be equal to the output voltage. Also, the height of the wave that you are generating, which is the amplitude of the wave, is likened and then equal or should be equal to the output voltage here, right? So that's how this function generator works. That's the function of the generator. So it's called function generator or signal generator. Okay, so the next thing we do is, for instance, let's say we are generating 101 kHz. 1 kHz. So we press this, we put this on 1, right? This has been connected. So we connect this, the cable positive side to this, to channel 1. So this is connected to channel 1 of the oscilloscope. So we'll be operating this volt per dive. This is what we'll be operating, not this, because this volt per dive, this particular one, is for this channel. The time per dive is common for both channels. So as to whether you are using this or this, you use the same volt time per dive. Now, although we have generated the frequency here, we are not seeing any signal until we press the kind of wave we want. So once we press this, we get the signal that we want. So this is the frequency or the waveform for 1000 Hz. Now, another thing we need to know is the volt per dive, right? The volt per dive works vertically. The volt per dive works vertically. So if I increase it, the height or the amplitude of the waveform increases, right? So it increases. If I decrease it, the height or the amplitude of the waveform decreases as well, right? Also, for the time per dive, we know time per second, the unit, and then this voltage. Time or period works horizontally, okay? And then voltage works vertically. Voltage works vertically. So if this one, the volt per dive works, if the volt per dive works vertically, it means the time per dive will also work horizontally. The time per dive works horizontally. This works horizontally. So when we decrease this, the distance between two cycles decreases. It means we've decreased the period, the number of oscillation per second. If we increase it, the distance between two cycles increases, right? If we decrease it, it decreases. When we increase it, it decreases. Okay. So that's a little bit for the oscilloscope. Now, another thing we need to note, this particular function where you see the arrow is called position. Now, the position, what it does is we have two positions for the two channels, right? So if you are using this channel, you are using this position. Now, this position, what it does is the position, if the waveform is here, right? If the waveform is here, maybe on this particular line, and then you want to put it on the next line, or you want to move the wave vertically, we use this to position the wave wherever you want to position it. And then we have this one, this position to this particular one, which works this way. That's why it's around where the time per dive is, because time per dive or time works horizontally. So if you also want to move this, the waveform here and here, this direction horizontally, we use this particular knob. Okay. Now, one thing is we need to know is the trigger, right? The trigger. Now, what the trigger does is when the waveform is moving, when the wave is not stationary and is moving, we can use the trigger button to stop it. We can use the trigger button to stop the wave from moving. We can use that one to stop it from moving. And then if we are displaying AC, then we have to put this on AC. We put this on AC as well because we are displaying AC. We are displaying AC, so we put it on AC. Now let's see how to calculate the amplitude. Now, on the oscilloscope, each box you are seeing here, you see those divisions on the oscilloscope. Each box you are seeing here, each box is 1 centimeter. So if you want to check the height of the waveform or the amplitude, right? The height or the amplitude, we count the number of boxes. So we have 1 box, 2 box, 3 box, 4, 5, and then there are subdivisions here as well. So that's 5.6 boxes. So that's 5.6 centimeters. 5.6. So that's the amplitude of this waveform or this signal that I've generated. That's the amplitude. Also, to calculate the frequency, let's look at how to calculate the peak-to-peak voltage. Now, what is the voltage from this peak, positive peak, to this negative peak? Now, the formula states that voltage peak to peak is supposed to be equal to the volts per dive times dive. Now, this dive is supposed to be the vertical divisions because we said that volts per dive. So this volts per dive times vertical divisions. Now, this vertical division is the amplitude that you calculated, the height of the wave. The height of the wave is supposed to give you the vertical divisions. So this is the formula for finding the peak-to-peak voltage. Now, how do we get this value? Now, this value is here, 1 volt per division. So for 1 division, we have 1 volt. Now, you can also check on the oscilloscope, right? You realize that if I turn this, the value here decreases, right? So the voltage that you are using here, the value is what you use as your volt per dive. So that's the volt per dive. So this volt per dive button, the value of this that you are using on the waveform is the one that you write. So we have, for this one, we have 1 volt per dive. So that's 1. And then this is the vertical division. We had 5.6, right? 5.6. And then, so when we multiply, we'll be getting 5.6 volts. Now, if you check, the value here, the answer here is almost equivalent to the value, the output voltage here. So this verifies that what work you are doing is correct. Now, to find the peak voltage, we are saying that if this is peak-to-peak voltage, to find peak voltage, what you do is to find peak voltage, we divide the peak to peak voltage by 2. So that gives us 5.6 over 2, which is supposed to be 2.75, right? 2.75 volts. Also, to find Vrms, root mean squared voltage, root mean squared voltage, Vrms, we multiply this V peak, the answer we had here, times 0.07. Now, this can also be written as peak voltage times 1 over root 2. Or this is the same as peak voltage over root 2. So this is the formula for finding peak to peak voltage. So the answer you have here, this particular answer, you multiply it by 0.707 or 1 over root 2. Or you can divide the answer by root 2, which is the same. So that's how you find root mean squared. That's how you find root mean squared. Now, to find the period, to find the period of this wave, they are saying that the formula should be time-based settings. So the time per dive is also called time-based settings. So to find the period, it's supposed to be the time per dive times the horizontal divisions, right? So the time per dive value is what you are seeing here. This is the time per dive. So as I said, when we decrease this, the value here changes. It means we are decreasing the distance between two cycles, right? So we are using, let's use this for the example. So the time per dive is supposed to be 0.5 millisecond times the horizontal division. Now, the horizontal division that we'll be calculating it only for one cycle. So the horizontal division will be for only one cycle. And then from here to here is one cycle. From here to here is another cycle. This is also another cycle. So in total, we have about 1, 2, 3, 4, 5 cycles here, right? But we only need one cycle, right? If we want to double it, we can just double it. So our calculations for this is based on only one cycle. So we count the number of boxes, and then this is occupying like 2 centimeters, right? The value is 2. So we have 2 boxes here. So this times this, 0.5 times 2 should give you 1, right? Should give us 1. So that's the period, 1 second, right? That's the period. Now, how do we find the frequency? We know that frequency equals 1 over period. So the answer we have here, we divide it. So this should be 1 millisecond, because there is milli here, 1 millisecond, right? So we find this 1 over period. So this will be 1 over 10 raised the 1 times 10. It should be 1 over 1 times 10 raised the power minus 3. And then that should give us 1000 hertz. Also, you realize that this value or this frequency that we are getting is equivalent to the frequency that we generated here, because we generated 1 hertz, 1 kHz. This is 1 kHz. Okay, so that's how you find the amplitude period, root mean squared, peak to peak voltage, frequency, peak voltage of a waveform, of an AC waveform. Thank you.